Okay, grade 12. In today's lesson, we're going to be looking at electric circuits. And we have this question 8 here. It says the battery in the circuit shown below has an EMF of 12 volts and an unknown internal resistance R. The resistance of the connecting wires and the ammeter is negligible. Then we can see here that we are given this diagram here. So let's observe what is going on here. You can see that switch S now is open. And then we have this resistor here. It is connected in series. But then as soon as we get to this part, we can see that this is a parallel branch because if we have to move our current, let's say if we have to close this one, then if our current moves like this, at this point, what happens? The current now has multiple pathways to flow. Right. So at this point, we are starting with our parallel branch because now the current starts to divide into multiple pathways. And then we can say this one is in a parallel branch. But then what is happening? The current moves like that. And then now it's not going to go to that part because this is only just a voltmeter. So we just assume that the resistance there is negligible. So even the current there won't be lost, right? So at this point, we can say that this one's and this one will be the combination, which will be in parallel to this one, because these two, we can say that they're part of the parallel branch, but then they're actually in series. So remember, I said whenever you have a case like this, just take these two resistors, make them a combination. So it's 8.4 ohms, right? So this 8.4 ohms, a combination of these two resistors, will be in series to this 6 ohm resistor here. And then we only have this resistor X here being in series, right? So this thing, this whole two resistors are parallel to the 6 ohm resistor there. So we have a parallel branch here. So this is what we call a series parallel connection. Then, okay, let's proceed with the question. We have switch S is open. 8.1 says write down the reading on voltmeter V1. So V1, if this is still open, we can see that V1 is connected in parallel to the battery. Therefore, it means that it reads the EMF, right? So whenever we have a voltmeter connected directly to the battery, we know that it reads the EMF if the switch is still open like this. Remember, when the switch is open, no current is flowing. The maximum energy or the maximum potential difference that you will have is the EMF when current is not flowing. So we have V1 being 12 volts. Then what about V2? Remember, current is not flowing, so that means we do not have any potential difference. We do not have any work done here. So that means the V2 here will simply read 0 volts. Then switch S is now closed. The reading on the ammeter is 1.2 amperes and the power dissipated in resistor X is 5.76 watts. Then 8.2 simply says define the term power. So let's run quickly to that. We say power is the rate at which work is done or energy is dissipated. Okay, then 8.3 says calculate the resistance of resistor X, and let's look at the marks. It's only 3 marks. So we know this should be easy. It should only be the formula, the substitution into the formula and the correct answer. So let's see what we are given here. We are given 5.76 watts, which is obviously our power, right? They even told us here, and the power dissipated in resistor X is 5.76 watts. So we know the formula for power. Because we are looking forward, what are we trying to calculate? The resistance, and then we are given the what? We are given the current here. So we have to use a power formula that has current and resistance. We know that the formula is P is equals to I squared multiplied by R. So our power is 5.76, and then the current that we have is 1.2 amperes, then square that and R. We can just simply divide both sides by 1.2 square and then 1.2 square. Then the R here, if you punch all this in your calculator, you will have 4 ohms, right? So this is the resistance in the series, right? It's only 4 ohms. The resistance of X, 4 ohms. Then okay, now they say 8.4, calculate the total external resistance. The total external resistance. So we know the total external resistance is one that is formed by taking the resistors in parallel, adding them to the resistors in series. So remember, we said this one is the only one that is actually in series, perfectly series. These ones, they are in series, but then within a parallel branch. So what do we do with them? We take them as a combination. So they become 8.4 ohms, and then which will be parallel to the 6 ohms. So to calculate for the parallel branch, we assume that we have 2 resistors here. So it's 1 over Rp and then 1 over R1 plus 1 over R2. So the R1 is 1 over 6 and the R2 is 1 over 8.4. Remember, we took it as a combination. And then at this point, to calculate our Rp, we know that we have to inverse this. And then the Rp, you punch that in your calculator, it gives you 3.5 ohms. But let's not get carried away. Remember, we still need to calculate the external resistance. So that's Rp plus Rs. So the Rp is 3.5, but then the resistor in series is 4 ohms. So add that together, that's 7.5 ohms. Right. Then, okay, 8.5 says calculate the reading on voltmeter V2, and that's for 5 marks. So we know that this will involve us having to use about 2 or 3 different formulas. Then, okay, let's check. They're looking for the reading on voltmeter V2. But first, let's understand what is V2. What component is V2 reading here? It's reading the voltage in the 6 ohm resistor, because we can see that it is connected in parallel to the 6 ohm resist. So it's only reading the voltage of the 6 ohm resist. Now, do not be carried away as to think that okay, since this ones and this ones, they are in parallel, that means they have the same voltage. Remember, this starts to be in parallel when we start to combine this here. So the 8.4 ohms. So the 6 ohm that we see here is actually in parallel to a combination of these resistors. Right, so it's parallel to the 8.4 ohm resistor, which is the resistance that is formed when you take these two and combine them together. So, okay, now we must find an angle as to how to solve this question. Let's check. Here we have the 4 ohm resistance, and then here we are given that this is 1.2 amperes. Now, since we have an ammeter reading here of 1.2 amperes, we know that even this resistor here will have a reading of 1.2 amperes, the current of 1.2 amperes. Where do we take that? We take it from the knowledge of saying if we have the total current of 1.2 there, the total current is equal to the current flowing in the series connection, but it is also equal to the current flowing in the whole of this parallel branch, right? So now that we have 1.2 amperes here, 1.2 amperes, we know that a combination of all these resistors will have a current of 1.2 amperes, which is equal to the current flowing in the series and the current that is flowing in the whole circuit, right? So now that we know that this is 1.2 amperes, we can actually use this to calculate the voltage that is flowing in the parallel branch, right? So let's calculate now. So to calculate the voltage in the parallel, we can say I of the parallel times the resistance of the parallel. So the I parallel is similar to the I series, it's 1.2. And then what is the resistance of the parallel? Remember, we calculated that one. We said it was 3.5 when we took the 6 ohm and the 8.4 resistance combined. Then 1.2 multiplied by 3.5, this gives us a voltage of 4.2 volts, right? So that's our V parallel. That's our V parallel is 4.2, right? Now, what is it that we know? We know that this voltage here will be 4.2 volts, but then also for the combination of this, the voltage will be 4.2 volts. Note, it is not the resistance of the 6 ohm resistor. It is not the voltage of the 6 ohm resistor. It is the voltage of the two resistors combined. So the 4.2 volt is the voltage of the two resistors combined. But now we are only looking for the voltage, for the voltmeter reading of only the 6 ohm resistor, right? So what can we do now? We can actually try to calculate the current that flows in this 8.4 ohm resistor. So let's calculate the current. We say, okay, to calculate the current of the 8.4 ohm, right? So we will have V over R, right? And then what is our voltage? Remember, it's 4.2. Then what is our resistance? It's 8.4. When we calculate that one, it will give us 0.5 amperes, right? But then why are we choosing this angle? We know that if this combination of a resistor has 0.5 amperes in total, and then we said that these two resistors are actually in series, then we know that if it is 0.5 amperes, this is 0.5 amperes, and this also here is reading 0.5 amperes. So by doing that, we have actually found the current that flows in the 6 ohm resistor. Therefore, now we can calculate the voltage by doing what? By simply writing the formula V2 is equals to I in the what? In the 6 ohm resistor times the R, right? So what is the current in there is 0.5. And then what is that resistance? Is 6, right? So when we say 0.5 multiplied by 6, that gives us 3 volts. Right. So this becomes the potential difference that flows in the 6 ohm resistor that we see here. So that means if we have 3 volts here, this is only to add up to that 4.2 volts. That means the 2.4 ohm resistor is only reading 1.2 volts. So this is how we got the 4.2, the 1.2 volt, and the 3 volts here gives us the 4.2 volts. So I hope all this makes sense. And then speaking in terms of that 5 marks, you can see that it is always proven that when you are dealing with a 5-mark question, you will either use about 2 or 3 formulas. So it has nothing to do with the difficulty of the question, just that there is a process into doing those questions. There is a process to you arriving to the final answer. So you can see we first calculated the V parallel, used the V parallel to actually calculate the current in the combined resistors, and then finally calculated the voltage flowing in there that is being read by voltmeter V2. Right, then 8.6 says a length of wire of negligible resistance is used to connect point P to point Q in the circuit. So now they're replacing these two resistors here. These two resistors that we see here being replaced by a connecting wire of negligible resistance. So it has a very, very low resistance to the point that we just assume that the resistance is 0. Then choose from increase, decrease, or no effect. Explain the answer. They say, how will voltmeter V1 be affected? Voltmeter V1 is here. But then remember, voltmeter V1 is no longer reading the EMF as we said here. Remember, here we said it's reading the EMF because the switch was still open. But now the switch is closed. So that means V1 is reading the what? The V external, the external potential difference, right? So it's reading the external potential difference. Okay, at this point, what can we say? If it's reading that, we can simply say, okay, let's check what will be happening in here. So if we close off this one, that means we'll only be left with these two resistors. These two resistors will now be connected in what? In parallel, right? But then we know if we have resistors in parallel, then what happens to our total external resistance? Our total external resistance decreases, because remember, in parallel, if you connect resistors in parallel, resistance has to increase. But then we know that resistance is inversely proportional to current. So what will happen to current? Current will have to increase. So we say total resistance decreases, but R is inversely proportional to current, so current increases. Now let's get to this part. We say internal voltage will increase and external voltage will decrease for a constant EMF, right? So our solution here is decrease because they asked us about V1 and then we said V1 is reading the V external, right? The external, the external voltage or external potential difference. Now we know the formula that goes EMF is equals to V external plus V internal. Now, if we say, looking at these formulas here, we have I times R plus I times R. Then we know the two components here that must be kept constant is IMF. So the two quantities that must be kept constant is EMF and what? Internal resistance. These two are always constant. You can never do anything to change the EMF or the internal resistance, right? So now the battle is in between the current and the resistance, right? So we said the total resistance or external resistance decreases, but what happens to current? Current increases, right? So at this point, you can see that there is an increase, a decrease, right? So we cannot really use this one as reference. But then here we only have the current. The current is doing what? Is increasing. This one remains constant. It remains unchanged. So this tells you if current is increasing, then what will increase between the V external and the V internal? It has to be the V internal, right? Because here we see there is an increase. So you cannot really reference with this one because remember here current is increasing but resistance is decreasing. So there will be a balance in here, right? And then now the V internal, if the V internal is increasing, in order for us to maintain the same EMF, a constant EMF, then what must happen? Then the V external has to decrease. Remember, they cannot both increase, they cannot both decrease. So if the V internal is the one that is increasing, then the V external has to decrease to maintain a constant EMF, right? So that is our explanation there. So we say total resistance decreases, number one, and then resistance is inversely proportional to current. So the current will increase, but then the internal voltage will increase and the external voltage will have to decrease so as to maintain a constant EMF, right? So our solution here becomes decrease because we are being asked about V1 and we said V1 reads the external voltage, which we can see here it's decreasing. Okay, then we have this question here. It says the circuit below is used in an experiment to determine the resistance of resistor X. They say the 12 volts battery has a negligible internal resistance. When switch S is closed, the reading on the ammeter is 0.5 amperes. Then 8.1.1 says state Ohm's law in words, right? So how do we state Ohm's law? Say Ohm's law states that the potential difference across the conductor is directly proportional to the current through the conductor at constant temperature, right? So you must not leave out that one, constant temperature. Then, okay, let's continue. We have 8.1.2 says calculate the resistance of resistor X. At this point, we can say that the 8 ohm and the X here, they are connected in series, right? So what is it that we know about the resistors that are connected in series is that current is the same throughout. Current is the same throughout. So current is unchanging, right? So if they say the reading on the ammeter is 0.5 amperes, so if this is 0.5 amperes, that means the current passing through the 8 ohm resistor is 0.5 amperes, and also the current passing through this X resistor here is 0.5 amperes. Then we can actually use this to calculate the resistance of X, right? Then by doing what? By simply using this, remember we are given the EMF, and then they said this one has a negligible internal resistance, right? So we can see there's no internal resistance that has been provided here. So that means we can simply use R is equals to V external over I, right? Then at this point, what is our total resistance? We don't know. What is our R external? And then, but our V external is 12. And then here we have a 0.5, which will give us an external resistance of 24 ohms, right? Then we can simply say the R external here is being made by the 8 ohm resistor plus X, right? So we have 24, 8 plus X, then we can calculate our X. 24 minus 8, then X is equal to 16 ohms, right? So it's just as simple as that. We calculate the total resistance by using the total voltage and the total current, and then we find the total resistance, use the total resistance to find X. Then 8.1.3 says, during the experiment, the switch is closed for very short periods of time. Give a reason for this. Why is the switch only closed for a period of time? It says to maintain a constant temperature for the experiment for reliability of results. So remember, Ohm's law states that we will only have the potential difference and the current being directly proportional if we make it a point that we maintain constant temperatures. So in order for to have our results being reliable or our experiments being reliable, we have to make sure that we maintain constant temperature for every part of the investigation. Then 8.2 says, study the circuit below. The battery has an EMF of 12 volts with negligible internal resistance. So also this one has no internal resistance. So you can see if internal resistance is there, you will be given, or they will simply draw a smaller block here, and then they indicate that R there. So here you are told that the internal resistance is negligible. That means it is not there. Then switch S is closed. They say 8.2.1, write down the potential difference across the 4 ohm resistor. So we can see that these are connected in parallel here. So we know that the 4 ohm resistor, if this is in parallel, what do we know about parallel connection? So for parallel, we know that voltage or potential difference is the same throughout. So we say voltage is the same throughout, which means for 1 mark, the reading on the potential difference across the 4 ohm resistor will just simply be 12 volts, right? And then 8.2.2 says calculate the reading on the ammeter, and that for 4 marks. Calculate the reading on this ammeter here. So how are we going to calculate the reading there? We can simply say for 8.2.2, let's first calculate the resistance here for these ones. So these ones are connected in parallel, and we can see that the ammeter here is reading the current in the 6 ohm and the 4 ohm resistor here, right? So you can see that this ammeter here is just connected right after this part here. So the current is coming like this, and then it splits to that direction, and then some of the current continues flowing in this direction. So the current that flows in this direction is the current that will be serving these 2 parallel resistors here. So that means the ammeter reading here is actually reading the current of these 2 resistors that are connected in parallel. So if we want to get to that, we can just simply calculate the resistance in between these 2 resistors. So by saying 1 over Rp is equals to 1 over R1 plus 1 over R2. So we say 1 over 16 plus 1 over 4, and then this will give us, so if we do that inverse thing, our Rp will give us 3.2 ohms, right? Then we can simply use that to calculate the ammeter reading, which is the current, right? So we say the current there will be, so current is V over R. So what is the voltage? Remember, our voltage is 12, and then our current is 3.2. Our resistance is 3.2. Then our current will be 3.75 amperes, right? Then 8.2.3 says calculate the energy dissipated in the 12 ohm resistor in 2 minutes, So we see this time here, we know immediately we might just say 2 times 60, and this will give us 120 seconds. So what are we trying to calculate here? We are trying to calculate the energy dissipated in the 12 ohm resistor here. So we want the energy dissipated in the 12 ohm resistor. But this two here, we can see that a combination of these two will actually be in parallel to this, right? So a combination of this, remember these two here are in series, right? So if we want to calculate the energy, then we can just combine these two here, and then they will give us what? 20 ohms. So we know this 20 ohm will be in parallel to the 16 and the 4 ohm there. So that means also this 20 ohm, as a result, this 20 ohm, a combination of it will have a voltage of 12 volts, right? Because it's in parallel, right? Then to calculate that, let's see, now we will have our V is equals to current and then times R, right? Then what is our voltage? Our voltage is 12. So we are looking for the current, but then the resistance, remember we took it as 20 and then divide both sides by 20. So let's find the current flowing in there. The current is 0.6 amperes. Now to calculate the energy, we know if we have current, we can use the formula for energy, I squared times R times change in time, right? Then what is our current there? It's 0.6, but then remember we are trying to calculate for the 12 ohm resist, right? We just found that a combination of this will have a potential difference of 12 volts, but then remember, since we found that the current is 0.6 amperes, for a combination of this, the 20 ohm, we know that since they are connected in series, they will share the same current. So this is 0.6 amperes, 0.6 amperes. So you can see it is still similar to the question that we just previously did. But then we are only focused on the 12 ohm resistor here. So we have current is 0.6 and then square, and then our R is 12, and then our time is 120. So when we multiply the two, we have 518.4 joules, right? Then 8.2.4 says the 12 ohm resistor is now removed from the circuit. How will the reading on the ammeter be affected? Choose from increases, decreases, or remain the same. Explain the answer. So now we are taking off this one. If we are taking off this one, we can see that this remains 8 ohm, 16 ohm, and 4 ohm. They're all in parallel. So remember, if we know very well, what did we say about parallel resistors? We say that current voltage is the same throughout, sorry. So voltage is the same throughout. So about this one, we said that voltage is the same throughout. So here they're asking us to explain how will the reading on the ammeter be affected. Choose from increase, decrease, or remain the same. So if we are saying that the voltage is the same throughout and nothing is done to the 16 ohm and the 4 ohm resistor, the 4 ohm resistor here, then the ammeter here will simply remain constant, because remember we said this ammeter here is not even involved here. This ammeter is only reading the current in the 16 ohm and the 4 ohm resistors. So these two resistors that are connected in parallel. And since the voltage will be unaffected, that means the current will be unaffected. Therefore, ammeter a reading of ammeter A there will not be affected. So the solution remains the same. Why? Because the potential difference across the resistors in parallel stay the same. So we are talking about that 16 ohm and the 4 ohm resistors. So if the resistance is not affected, the current is not affected and the voltage is not affected, then nothing can happen to that ammeter reading. Awesome.